Hello and welcome to lecture 17 of our Essentials of Semiconductor Device Physics course. In this lecture we're going to derive an equation which will lead to the important concept of diffusion length, and that we will also use later to derive Shockley equation. Last time we derived these two equations. These equations are applied for free electrons, these equations are applied for holes, but they are all just a mathematical statement that what comes in minus what's left minus what dies is what stays. And this is applied for electrons and this is applied for holes. Now in this lecture we're going to show a quite important application of this equation, and we're going to consider a physical situation that will appear later in the course when we deal with currents in diodes. And the physical situation is the following. We're going to suppose that there is some current of holes. I'm assuming here holes, but I could have assumed the electrons. It doesn't really matter. And this can be any current. It could be drift, diffusion, or a combination of both. But after some boundary, we know that the current is only by diffusion. How do we know that? Will become apparent when we discuss currents in diodes. But for now, we can just assume that the current in this region is only by diffusion. And also that there is a loss mechanism. So there is the recombination process we discussed last time. And we can also assume a stationary regime, which basically means that nothing changes in time. So things are constant in time. And our job is to find an explicit expression for the spatial dependence of the concentration of holes in the region where transport is only by diffusion in the presence of a loss mechanism. Okay, so we can focus our attention on this equation now because we're dealing with holes. So if we're assuming that nothing is changing in time, then that means that this term is zero. And if this term is zero, then this equation is reduced to this equation. Now, from lecture 15, we learned that the current density, if the current is by diffusion, then the current density is given by this expression, where d is the diffusion coefficient. And in lecture 16, we saw that the concentration of charge is given by this expression, where this is the elementary charge and P is the concentration of holes. So we can use this expression here, and then we get this expression for the current density. And in our equation we have the derivative of the current density. So when you take the derivative, we already have a derivative here, so we get a second derivative. Okay, so moving this term to this side, we get this expression, and now we can use this equation for the derivative. We have a negative sign here and also a negative sign here, so they cancel. We get a positive sign, and then we can move d to the other side and cancel the q's here, and we get this differential equation. And the solution to this equation is a sum of exponentials. We have the square root of the denominator here because we have two derivatives, and we can have also negative or positive signs. So you can check for yourself that if you take the second derivative of p of z using this expression, it gives p divided by d tau. It's very straightforward to do that. Now to find a and b, we need to apply the boundary conditions. So one boundary condition we have is that we know, because of the recombination process, that the concentration will decay as we move away from the boundary. So the limit that the coordinate z goes to infinity, we need to require that the concentration goes to zero. Now, since the exponential here has a positive term, as z goes to infinity, this term will blow up. So to avoid that, we need to have b equals 0. So b equals 0 is the condition we get from our first boundary condition. So using the first boundary condition, our expression is reduced to this term with only one exponential. Now, the second boundary condition, we can use the origin. So we know that p evaluated at the origin must be equal to a, because we're going to have 0 here, then this term is going to be 1. So we can, instead of using a, we can use p evaluated at the origin. So this is basically the job we had to do. We found that when transport is by diffusion in the presence of some recombination process, then the concentration of particles decay exponentially with space. Now it's useful to express or define a criterion for a typical distance that the particles travel before they suffer recombination. And to do that, we can notice that when we evaluate the concentration of particles at the distance given by the square root of the diffusion coefficient times the lifetime, then we're going to replace z with this term, then we're going to get p naught times the exponential to the power of -1, which means that the concentration evaluated at this point is the original concentration divided by Euler's number. So this is a quite useful and common criterion used to express a typical propagation distance that the particles can experience before they suffer recombination. So if we locate this point here in the plot, this will be the point where the original concentration reduced by this factor. So we can say that the typical distance the particles propagate is given by the square root of the diffusion coefficient times the lifetime. And we can use this distance to define the diffusion length. So the diffusion length, by definition, is the distance the particles propagate until the concentration drops by the 1/e factor. So the diffusion length is the typical distance particles propagate in a regime where transport is by diffusion and there is a loss mechanism. So we can use the definition of diffusion length to recast this equation in this form, and we're going to use it in a future lecture when we derive a Shockley equation, but I'm going to remind you in that lecture of where it came from. And with that, we conclude not only this lecture, but chapter 1 of the textbook. And in the next lecture, we're going to start talking about semiconductors in the context of the very important band theory. So I see you next time. Bye bye.